Good morning, class. Welcome to Wednesday in week 6. This is week 6 of the semester. So, hope you guys are doing all right. We you had a homework problem set that was due tonight, and I moved the due date till Friday. I gave you a few extra days, and I think that most of you were doing all right in the homework set. So if you look at the syllabus, we're supposed to be starting work and energy today, and so that's a new unit, and we're going to spend one more day talking about Newton's laws for now, and we'll do some clicker questions at some point in the future. But hopefully we can start talking about these new concepts of work and energy today before our time is up. So we'll try to get there. So I hope you guys are doing all right. And if you guys have any questions, throw them up in the comments as we're working here today. And I'll try to answer them. Anything else come to mind right now? I think that's it for now. All right. So let's get started. All right. So air drag. Good morning, Holly. Air drag is a force that is it's a kind of friction. It's a kind of friction. So you have you think of you have a problem in the homework that involves a raindrop falling through the air. So let's frame our discussion around what's happening to a raindrop as it's falling through the air, and the physics of this problem turns out to be really interesting in terms of, the dynamics of the raindrop depends on the size of the raindrop, more specifically its radius. Okay, so that'll come out of this work today. All right, so let's take a look at this problem that was assigned, and then we'll go to the whiteboard and take a look. So did you see? It's due Friday now. All right. Nope. Here it is. So this says, calculate the speed in meters per second a spherical raindrop would achieve falling from 4.8 kilometers in the air in the absence of air drag. And then what is the speed with air drag? And then they give you some parameters. For my problem, the raindrop is 7 millimeters across, so that would be its diameter, not its radius. Its radius would be half that. It has a density of 1,000 kilograms per cubic meter. That's the density of pure water. And surface area is something you could look up, pi r squared. So that's the surface area is cross section. So if you have a sphere, what's its cross section? A circle, pi r squared. And assume the density of air is 1.21 kilograms per cubic meter. Just to remind you guys, when you're working on problems here, don't forget you can click the link to the ebook. And this is such a handy feature. It takes you right to the section of the textbook that is relevant. So this link takes you right to the drag force and terminal speed, whatever that is, section in the textbook. And it talks about drag forces. There's a formula up here, and gives you a table of coefficients, drag coefficients for a variety of objects. And so this is sort of like, what is a drag coefficient? It's kind of like the coefficients of friction, in that the material, but also the shape of the object influences how much drag it has. Drag suits, and there's some mathematics deriving what's called terminal velocity. So we'll take a closer look at that on the whiteboard when we get to it. All right. So back to the problem. Don't forget, you guys should be reading this textbook. There is way too much material for me to communicate to you via, official, lecture time. There's not enough lecture time for me to teach you everything that you can learn. Read the textbook, and then the lectures are going to be much more valuable to you. You're gonna get a lot more out of it. You see material for the second time, or you hear an explanation or a discussion of some topic from a different perspective, a different angle. That's when you really start to gain understanding. All right, so calculate the speed. All right, so the first part of this problem is a situation. Ooh, don't want to rotate. Okay. No, I don't want tablet mode. So the first part of this problem is a free fall problem. It says, you have a raindrop and it falls a distance. Let's say it starts at 0 and falls a distance equal to, for me, it was 4.8 kilometers. So y final is 4,800 meters. And it's a free fall problem. There's no air drag, so the acceleration that this raindrop will experience is the acceleration due to gravity, 9.8 meters per second squared. We'll call it down positive since it's falling that way. And so if it starts from rest, the initial velocity is 0. Let's get rid of that. V naught equals 0. And you're asked to find, well, how fast is it traveling when it gets to the ground? So this is a kinematics problem. The most direct route to the solution here is to use this kinematic equation of motion, which has V naught, V acceleration, and delta y, y minus y naught in it. And so if you solve for V here, the initial velocity is 0, initial position is 0, so the final velocity is going to be the square root of 2 times the rate of acceleration times how far it traveled. And so when I plug in 9.8 and 4,800 and multiply by 2 and take the square root, I get 307 meters per second. So that's telling us if there are no air drag, raindrops will be pelting us here on the ground at like 300 meters per second. And that might kill you. That's really, really fast. And so it's a good thing that we have an atmosphere to slow. I guess if we didn't have an atmosphere, there wouldn't be any raindrops anyways. But it's an interesting problem that the velocity of the raindrop would be 300 meters per second if there was an air drag. The answer here doesn't depend on the geometry of the raindrop either. It could be a big raindrop, small rain. It could be a snowflake. It could be a piece of hail, and the terminal velocity would be the same. It doesn't depend on the mass. It doesn't depend on the geometry, the cross-sectional area, the volume, any of that stuff. So that's the answer to the first part. And the second part says, well, what if there is air drag? So now it becomes a situation where in order to find the answer, we got to use Newton's second law. So we got to think of the raindrop as an object on which forces are exerted. So the reason it's falling is because the raindrop has a weight, a force of gravity, equal to its mass times the acceleration due to gravity. And air drag is a force that opposes the let's call that F sub D, like your textbook, the force of drag. And let me zoom in here a little bit. What exactly is happening here? So as the raindrop is falling through the atmosphere, the air, it's sort of plowing through the air as it falls, and that creates friction. So the air is actually rubbing against the outside of the raindrop, and that's friction. That slows it down. So if you zoom in and you think about what's actually happening with air flowing around the raindrop, then it makes sense that the size of the raindrop would matter. What's gonna influence how strong this drag force is? The size of the raindrop, and by size it means probably the volume, but also the cross-sectional area. Probably both those things matter. What else matters? Probably the density of the fluid. Air is a fluid, just like water, and it flows around this falling object. And how dense that material is probably matters. If the raindrop is falling through the atmosphere versus a pebble falling through a column of water, which of those fluids, water or air, is going to supply more resistance to the flow? Water. It's denser. Okay. So, all right. Zoom out here again. And when you look in your textbook, there's a force law given for the drag force. And it looks like this. There's a 1/2 coefficient, there's a constant C, there's a constant rho, there's a value A, and then there's a V, and it's squared. Okay, so what do all these things mean? Well, C is the coefficient of friction, or drag coefficient. Sorry. It's like a coefficient of friction. And so this thing depends on the geometry of, go back to our ebook here. And we got this table. It depends on the geometry of the object. Toyota Camry has a drag coefficient of 0.28. A sphere has a drag coefficient of 0.45. So here we're told that the raindrop is spherical as it's falling, and we think of raindrops as being sort of teardrop shaped, but actually as they're falling, the surface tension of the water pulls all the water in and creates a sphere. So it's pretty spherical when it's falling. So that's a good approximation. So for our problem here, C is 0.45. That's our drag coefficient. Rho here is the density of the fluid that the object is falling through. So for our problem, it's given to us the density of air. It says assume the density of air is 1.21 kilograms per cubic meter. A is the cross-sectional area of the object. So for our problem here, A is the area of a circle, which is the cross-section of the sphere. And V is speed of the object. So this is interesting. Remember yesterday in the lab session I was telling you that there's force laws that describe forces that are positionally depend on the separation between objects, like gravity, and next semester we'll see the electrostatic force. And then there's forces that depend on velocity, air drag. The faster an object goes, the more air drag it experiences. So what's an experience you've had? Driving down the highway, put your hand out the window, put your hand out the window, there we go, and you hold it flat, you feel more air drag. You hold it like this, you feel less. What's the difference? Cross-section, cross-sectional area. Why does your hand like this experience more air drag than like this? Because here it has a greater cross-section. That's A. A is bigger. Driving fast, driving slow, you feel more air drag when you're driving fast. That's V, speed. Okay. And okay, so an interesting thing happens here, and let's say it in words first. It goes something like this: as V increases, the force of drag also increases until it is equal to the weight. Then what happens? Well, if it's equal to the weight, what you have is a situation where the net force, which would be equal to the weight pulling down, it's called down positive, like we did over here, minus the force of drag opposing it, which is mass times acceleration. If it stops speeding up, there's a point where the net force is equal to 0. So as V increases, Ft increases until it's equal to the weight. And at that point, the net force is equal to 0, and the drag force is equal to the weight. And the V, the speed, where this happens, is called, anybody know? Let's see. Anybody know? So and think of a skydiver. The skydiver's falling, and the moment the skydiver leaves the plane, the drag force is pretty small, and the skydiver's weight pulls them down. And at some point, the drag force, which gets bigger and bigger and bigger as the skydiver's speed gets bigger and bigger and bigger, eventually the drag force is equal to the weight. And that means the net force is 0, and that means there's no longer acceleration, and that means V is constant. What's that called? I always got it. Terminal velocity. It's called terminal velocity, or terminal speed. Okay? And that's what part B of this problem is getting at. It's like, well, you are assuming the thing is falling fast long enough. The raindrop has been falling long enough to reach terminal velocity, and that's a pretty good assumption if it's been falling for 4 kilometers. And then what you do is use Newton's second law right here with the forces in play and solve for V. All right, so what does that look like? It's going to look like this. The net force on the raindrop equals its weight pulling down minus the drag force pulling up, and Newton's second law, so that equals mass times acceleration. But if you're at terminal velocity, that net force is 0. So the weight of the raindrop is equal to the drag force it experienced. Weight is m times g, and drag force is 1/2 c rho a v squared. And you solve for v, and that gives us terminal velocity. So let me rearrange this. V, so 2mg divided by c rho a square root. Okay, so you can solve for the terminal velocity. So here, let's do a little bit more algebra for this problem, because what we're not given the mass of the raindrop, but we are given the density of the raindrop. So mass is equal to density And so here I got to put a subscript. This is a different density. This is the density of air over here. That's the density of the fluid through which the airdrop is falling, times volume, the volume of the raindrop. So volume times density gives you mass. And what's the volume of a sphere? It is, gotta remember this, 4/4 pi r cubed. Okay. So I could put that in for mass over here. What about A, cross-section? Cross-section is pi of a sphere. The cross-section of a sphere is a circle. So the area of that circle is pi r squared. So let's put that in this those two things in this expression and simplify and see what we get. So we get V equals big radical sign 2. The mass of the raindrop is its density times its volume multiplied by G, and then divide by the coefficient of friction of drag, which we look up in a table, times the density of air times the area, cross-sectional area of the raindrop. So what we get here, let's see, let's simplify things. We get a pi up top and down low that cancels. 2 of the r's in the numerator cancel. So this simplifies to, erase some of that. This simplifies to terminal velocity equals the square root of 2 times the density. Now let's multiply the 2 through. So let's see, 2 times 4 will give us 8 times the density of water times G divided by, bring the 3 down low. Oh, there's an R up here too. Times the coefficient of drag times the density of air. All right, so we get this this formula from Newton's second law when we think of densities instead of, and the geometries instead of mass and area. And so what do we got here? We got the terminal velocity depends on is directly proportional to the square root of the density of the fluid through which the raindrop, or directly proportional to the density of the object. Okay, that makes sense because that makes it heavier. Depends on G, that makes sense. It depends on the radius of the spherical raindrop. And it's inversely proportional to the square root of the density of air. So if it was falling through air that was more dense, its terminal velocity would be less. And okay, so I wanted to derive that because this is an interesting result here. We got the terminal velocity is a function of the square root of the radius of the raindrop. And you know, why is that interesting? It's because if you think of, like, let's think of something different, hail. All right, spherical hail drops, hail particles, whatever, falling from the atmosphere. And you know, if you have small hail, little ice balls, you know, that's not really that much of a risk. But if you have larger chunks of hail, they can do some serious damage. And there's 2 reasons for that. It has to do with the fact that individually they're more massive, but also individually they're traveling faster. They're moving much faster. All right. In fact, we'll learn a little bit later that the energy of an object, a moving object called kinetic energy, is proportional to its speed squared. So if you double the speed of something, you actually quadruple the amount of energy it has. So large hail is very dangerous. It can cause property damage, but it can also just be crop damage, but it can also just be dangerous to people and animals. All right. So I think that's enough about that problem. Anybody have any questions about that situation? Put it in the comments, and we'll take a look. But I think that you can handle that problem now. I won't go through. So I calculated the results for the parameters that were given to me for the diameter of the raindrop, and what I get is, again, up here without air drag, the terminal velocity is over 300 meters per second, and without air drag, the velocity is 300 meters per second. With air drag, the terminal velocity is 13 meters per second, which is a lot less than 300 meters per second. So air has a significant impact on the way that raindrops fall. It kind of brings me back. Remember when we were learning about free fall, I said, we can learn about free fall thinking about how objects fall in the absence of in the absence of air drag, in the absence of friction, air resistance, whatever you want to call it. And it's a useful exercise. And there's certain things in the real world that we can model like that, like rocks falling down wells, balls thrown up in the air and coming back down. But this is an example of a situation where if you want to understand how raindrops behave when they're falling, you cannot model that as free fall. You have to include the effect that air drag has on that object. Otherwise, the knowledge you gain is completely just doesn't apply to the real thing. So buried in here is a lesson about how physicists work. When physicists are trying to model the world, we tend to think of systems as onions with lots of layers of complexity. And the goal is there's a trade-off. There's a trade-off. If you add layers of complexity, that makes the problems harder to solve and model mathematically or computationally. And when you add those layers of complexity, it also obscures or makes it harder to understand the fundamental characteristics of the system. What factors of the system, what properties of the system matter the most for determining how it behaves or what it does. And so on the other hand, if you don't have enough complexity, the solutions you get, the knowledge you gain from studying that system is completely unreal. It doesn't reflect the real situation at all. So there's a balance. It's kind of like a tension. You want to add layers of complexity as needed so that the solutions that you arrive at are actually good approximations to the real thing. Otherwise, they don't tell you anything. But at the same time, you want to peel away layers of complexity that aren't needed to give you the degree of accuracy or understanding that you need, because that makes solving the problem easier, and it also probably means that the result you end up with gives you more insight into the dynamics of how the system works. Like in this case, adding the air drag, solving for terminal velocity, we get insight into the way that raindrops or any spherical particle falling through the atmosphere, how it behaves. We find that its terminal velocity is proportional to the square root of its radius. And we can apply that to raindrops or hail falling from sky, or ice balls, or bowling balls. Okay. All right. That's enough on that problem. So let's start talking about some new stuff. And let's talk about a new physical quantity called work. And I guess there's a couple ways we could proceed. Let me define what work is in terms of physics, and then we will explore how it's connected with stuff that we already know for a simple system. So work. Work is, in words we can say, work is a force applied over a distance. Okay. And I don't know, that's not the, that's a definition you might find in a textbook. And for me personally, it doesn't really tell us that much. It's sort of, the reason that you would see a definition like this in a textbook is because it gets at the mathematical way that you calculate work. Work equals a force applied over a distance or displacement. It's probably better to say displacement. Work equals force over a distance or displacement. So the way you calculate work is by taking the force that's doing the work and multiplying by a delta x or delta y or delta r, some measure of distance or displacement. And but so what we wrote down here, it's gives us a way to calculate what work is, but it doesn't really tell us what its significance is, at least not yet. And there's more to it though too. It's like if if I have a box or a shopping cart, something, and I'm pushing on it, so there's a force exerted on this shopping cart in this direction, and I want to know how much work that force does over some distance, delta x. It's very straightforward. The work equals the force times the displacement, delta x. But what if, I don't know, let's say that, same situation, you have the shopping cart, and now there's a little kid pushing the shopping cart. So little kids are short. They don't have arms that long. That's really bad. But now, the kid's going to be pushing up and to the right because they're short. And as the shopping cart rolls along. So now, what is the work done by that force? And this is more complicated, and what comes into play here is the fact that these two quantities are vector quantities. And so let me draw this picture a little bit more carefully over here. So if you have a force vector that looks like this, and a displacement vector that looks like that, and you want to know how much work that force does, turns out that the part of the force that matters, this force would have a component that is parallel to the displacement and a component that's perpendicular to the displacement. Call that F parallel and F perpendicular. And it turns out that when you're calculating the work done by that force, the only thing that matters is the component of that force that's parallel to the displacement. It's red there. Okay, and so we think about this in terms of the geometry of the situation. There's an angle between the vectors here, the force vector and the displacement vector, and if we flesh that out a little bit more, what we see is that this component of the force that's parallel to the displacement vector, can be gotten by taking the total force and multiplying by the cosine of that angle between the two vectors. So over here we would have work equals F cosine theta delta x, or we can move the cosine to the end. Okay, and this type of thinking, where you have, another way to think about this is you have a vector. Here we go. Very, very sophisticated props here. You have two vectors that look like this. My silver pen is the force, the blue pen is the displacement. This force is doing work along the direction of displacement, but that work only depends on the component of the force that is in the same direction. Another way of saying that is the projection of the silver pen onto the blue pen. What that means is, it's like if I rotate things, or imagine this, I have a light above shining down on this system. That light is going to cast a shadow of the silver pen onto the blue pen, and the length of that shadow is the same as the component of that force that's in the direction of the displacement. So there's a mathematical operation that accomplishes this projection of one vector onto another, and it's called a dot product or a scalar product. So another way to write out this expression for work, let's use black, is it's the dot product between two vectors, and that's equal to the magnitudes of those vectors times the cosine of the angle between them. Okay, so here we have a more careful, more complete way of writing down what this quantity is. Okay, so we're just defining a new quantity here. We're not giving it much context for why it's important. We're saying work is a force applied over a displacement, or more carefully, it's a component of a force that is parallel to a displacement. It's the product of the component of the force parallel to the displacement and the displacement. So with this formula, we can calculate how much work a force does. Okay, and what units would we get? We would get what's a product between force, which is units of newtons, times the displacement, which would have units of meters. So the unit of work is Newton meters. Newtons times meters. Okay, and that's also called a joule, or J for short. So 1 Newton meter is equal to 1 joule. All right, so we got 11 minutes. Let's keep going here. Let's see if we can gain some insight into what this quantity represents by asking. Let's set up a scenario like this. There's a shopping cart, and you're pushing it down the aisle in a in a grocery store, and the only force, of course, in the real world, there'd be friction in the bearings of the wheels, especially if it's a Walmart shopping cart. It's probably very wobbly and squeaky. And we're going to say there's no friction, there is no air drag. The only force, and of course in the vertical direction, everything's balanced. There's a normal force exerted on the shopping cart by the floor, and then there's the weight of the shopping cart, gravity pulling down the cart, but those two forces balance, so we can ignore what's happening vertically. So we're just going to focus on what's happening horizontally, and there's just one force, this applied force of the shopper pushing the shopping cart. And then let's think about a force, this constant force applied over some distance, and that force causes an acceleration. That acceleration causes a change in velocity. So let's see if we can connect up this new concept of work with these previously learned concepts of acceleration, forces, and kinematics, velocities, things like that, and see what kind of relationship we get. Okay, so again, the situation is there's a shopping cart, and someone pushing the shopping cart, and then there's an applied force, F, in the horizontal direction, and that's it. That's the only force that matters. And the shopping cart goes from some initial position to some final position. It has some initial velocity, which we could say is 0, and it accelerates to some final velocity. It goes from point A to point B, from velocity 0, velocity 1 to velocity 2, v naught to v. And we want to see how this connects up with this concept of force, this concept of work. All right, so it's all one-dimensional here. So when it comes to work as the dot product between these two things, we can ignore the dot product because the angle between, I'll draw it here, the displacement vector and the force vector, they line up. So the angle between them is 0, cosine of 0 is 1. So the work done by this force is just F delta x. Okay. Now let's think about Newton's second law. The net force on this shopping cart is just this one force, and that equals the mass of the shopping cart times its rate of acceleration. And let's see if we can figure out some kinematic equation. All right, so then if we put this in here for work, we have work equals F delta x, and that equals mass times acceleration times delta x. And so let's see if we can get rid of acceleration in delta x and replace it with velocities. So let's see, kinematic equation of motion. We got this one, v squared equals v naught squared plus 2a delta x. Well, we're not used to seeing it like that. It would be x minus x naught in this case. That's one of our kinematic equations of motion. So if we solve this, so this is a delta x. If we subtract the v naught from both sides, we get 2a x minus x naught is delta x, and then divide both sides by 2, we get 1/2 v squared minus 1/2 v naught squared equals a times delta x. So we have this expression right here, which is equal to a delta x. We can plug it in up here, and let's see what we get. So we get work equals F delta x, which is ma delta x, which is m times 1/2 v squared minus 1/2 v naught squared. Let's multiply that through. We have work equals 1/2 m v squared minus 1/2 m v naught squared. Okay, so now we have a connection between this new concept work and old concept of velocity. Well, what is that actually telling us? Well, we have there on the right hand side of this equation, there's two terms that look identical except for v. So that's and the things that are in there are a 1/2, a mass, and then a velocity squared, or a speed squared. And you can think of it as a speed here because everything's one-dimensional. And So what we have here is a quantity which we've discovered. Let me write it out in words. Oh, come on. Kinetic energy. Okay. Kinetic energy is defined as 1/2 mv squared. And so now we have two new things. We have this new thing called work, and we have this thing called kinetic energy. But what we've discovered here is there's an equivalence between the two. Well, there's not an equivalence. There's an equivalence between work done and, let's look at this right-hand side a little bit more carefully. You know, what is this right-hand side over here? It's a change in kinetic energy. It's like, you know, what we have here is work equals, the first term is the final kinetic energy, and the first term has a V naught in it, so that's initial kinetic energy. So work equals change in kinetic energy. And so now we have a relationship which is it's meaningful. We have a connection between this quantity we call work and this quantity called kinetic energy. Well, what is kinetic energy? It's the energy an object has by virtue of its motion. And what we've discovered here is that if there's one force doing work on an object, and that's it. It's in isolation, and so it could be a net force. It could be the sum of all forces. It's probably better to think about it that way. And this net force causes an acceleration. The effect that it has is to change that object's kinetic energy. This is how I would think of work then. Instead of thinking about work as the force applied over a distance, I think of work as this. Work is the physical quantity that we can calculate, but what's its connection to the real world? When work is done, what's happening? Objects are gaining or losing energy, or there's some form of energy that's in the process of changing forms. It's changing from one form into another. And we got one piece of this now. There's more complexity to build on top of this. We've discovered one version of, let's call it the work energy theorem. Okay, so this is right here, the work energy theorem, and it's probably better to think of this as the total amount of work than the work done by one force. It would look exactly the same if we thought of this as a net force instead of just one individual force. The work energy theorem. All right. So that's enough for today. This is a lot of new material, but there is a really powerful feature of this new quantity work, these new quantities of work and energy. So one thing is we said that the units are Newton meters or joules for work. Since there's an equality between work done and change in kinetic energy, that means the units of energy are also joules, Newton meters, joules. So joule is the SI unit for energy. Of course, there's tons of other units of energy out there. There's kilowatt hours, there's BTUs, there's barrels of oil equivalent, there's calories, there's kilocalories, there's many, and there's unit conversions between them. But the SI unit of energy is a joule, and so we see that connection. The other thing is calculating work is the dot product between two vectors, and the result of a dot product is a scalar. It's just a number. It can be positive or negative, but it's just a number. It doesn't have direction associated with it. And so when you're working with work and energy, the fact that the quantities you're working with are scalars instead of vectors means that, one, you lose a little bit of information. You lose information about direction of quantities, but what you gain is simplicity. It's much easier to work with numbers. It's just like accounting then. You're just adding up numbers. Some are positive, some are negative, but it's just a sum. It's just a straight arithmetic sum when you're dealing with those things. All right, so that's enough for today. I will see you guys on Friday, and that's when the problem set is now due, and then I'll be posting a new problem set sometime in the next few days. So I will see you guys next time. Any questions before I go? I'll give you a minute before I stop the stream. The delay is large today. All right, don't see any questions, so that's it for today. I'll see you guys next time. All right, have a nice